we are going to continue our conversation about storing files on a tape. Last time, we talked about how we can do this greedily with the aim of optimizing for the expected cost. And the reason for that was because we didn't really have any information about how we expect the files to be accessed, in what order, with what frequency. So we just assumed a uniform random distribution on file access and optimized for the expected cost based on this assumption. Now in this video, I want to focus on a slightly different setting. Here we assume that we are actually given precise information about how often the files will be accessed. So associated with each file fi, we have a frequency which I denote by little fi. And that's the number of times that we know that this file will be accessed. And now we can update our cost function to reflect the total cost of accessing the files as opposed to the expected cost, which is what we worked with last time. So as you can imagine, the total cost of accessing files, if they are ordered according to pi, is simply the total amount of time that it takes to access each file multiplied by its respective frequency. So the first file will have a cost of access proportional to its own length multiplied by the frequency with which we know it is going to be accessed. For the second file, it's going to be the length of the first and the second file combined multiplied by the frequency with which we know the second file will be accessed, and so on and so forth. So that's essentially what we have here in notation. What we are saying here in this expression is that for the kth file, look at the frequency with which we know we are going to access this file, and this expression here captures the cost of each of these accesses. We can pull out the summations and we are staring now at this double sum, which captures the total cost of access. Feel free to take a moment here, pause the video and make sure that this cost expression makes sense, because this is what we will be trying to optimize. So let's make our key question explicit again. Notice that what we want is an ordering that minimizes the total cost, which is a function that we just saw a few moments ago. To develop some intuition for what's going on here, let's spend a couple of minutes looking at some special cases. So the first special case I want to focus on is when all the file lengths are exactly the same. In this case, I claim that it makes sense to sort by frequencies, and specifically I'd like the most frequent file to show up first. To see why this makes sense, let's go back and look at the cost function again. Now, when you think about the setting when all the file lengths are the same, notice that no matter how you permute the files, this expression here is going to remain exactly the same. So you can really think of the ordering as supplying a fixed set of weights to the files as you go along. Specifically, the first file will have a weight of s if s is the common file length of all the files. And the second file in the ordering will have a weight of 2s. The third file will have a weight of 3s, and so on. So now it's just a matter of figuring out which frequency do we want to associate with which weight. And it should come across as natural that you want the highest frequency to be associated with the lowest weight and the smallest frequency to be associated with the highest weight. So this is the reasoning for why we want to order files according to decreasing frequencies. So this is a good time to pause and reflect, especially if you have a pen and paper handy. Feel free to attempt proving the correctness of this approach a little more formally than what we have just discussed. In the meantime, let's go ahead and look at a different sort of a special case. What if all the frequencies are equal? This should strike you as being similar in spirit to the scenario with the uniform distribution that we studied last time in the context of expected cost. It's just that in this setting, We are not saying that we don't know how the files will be accessed. We are saying that we know them to be accessed uniformly frequently, that is. So you can imagine that each file is being accessed exactly once or exactly twice, or exactly s number of times for your favorite value of s. The argument is going to remain the same. What we would like in this situation is for the shorter files to come up first. So in particular, just like we did when we were trying to optimize for expected cost, we want to organize the files in increasing order of length, and that should take care of it. Once again, doing the formal reasoning to establish the correctness of this approach is very similar to the reasoning that we have already gone through for expected cost. So please feel free to once again take a pause and work it out for yourself if you'd like to be sure. But now, having looked at these two special cases, we want to move on to talking about the general case where we make no assumptions about either the frequencies or the lengths being equal. And so far, the intuition that we have built up tells us that the high frequency files should show up earlier and the shorter files should also show up earlier. But sometimes you may be conflicted about what if a file is high frequency and is long, or what if it's a short file but it's very low frequency. Where should we position these? This is not entirely obvious. So what we want to do is come up with some sort of a function of f and l, which is the frequencies and the lengths. And what we want to do is have this function behave in such a way that it can guide us through the placement of the files. So if this function takes a smaller value for some file compared to another, then that file should be placed earlier in the ordering. And as you can imagine, what you want for this function to do is to prioritize the high frequency files and prioritize the short files somehow simultaneously. And yet again, this is a good place to pause and ponder. See if you can come up with a few candidate functions that have this sort of a behavior, and see if you want to try and prove that they actually work in terms of predicting the correct optimal order. So here is one first cut at such a function. I'm going to propose L minus F, where L is the length and F is the frequency. So the hope is that if you have a high frequency, you get a large negative score, which pulls up the corresponding file because it has a lower score. And if your lengths are large, that's going to bump up the value of the function and it'll push those files further down the order. So this is a function that seems to associate smaller values with high frequency files and also smaller values with shorter files as well. But as it turns out, unfortunately, this function doesn't quite work as we would want for it to. And here is one example to illustrate this. So consider the scenario where we have two files. The first one has a length of 3 units and will be accessed only once. So the L minus F value for this is 2. And we have a second file which has a length of 5 units and will be accessed twice. And the L minus F value on this is therefore 3. So if we want to organize the files according to smaller g values first, then file A will show up first and file B after that, at least according to the algorithm. And in this case, notice that the total cost is going to be 3 for accessing file A once and 2 times 8 for accessing file B twice, because you now have to access A to be able to access B. So the cost of accessing B is 8 and you're going to access it twice. So 8 times 2 is what you get for the cost of accessing B, and that gives you a total cost of 19. Whereas the optimal order actually would be the opposite, where you place B first and position A after B. This gives you a total cost of 18 because you have to only pay 5 units of cost for accessing the first file, which is B, and you access it twice. So the total cost happens to be 10, and you access the first file, well, the file that was first in the other order, you access that only once, and this time you pay for it with a cost of 8 because you have to access B this time to access A. But nevertheless, it adds up to 18, which is less than 19. So this is an example of a function that does not actually work. So one of the reasons that we went down this dead end to explore something that doesn't work is so that I could have an excuse to serve you the periodic reminder that we should be extremely careful when working with greedy algorithms. Sometimes ideas that just about sound right or feel intuitively appealing may not actually work out in the end. So you have to be super careful and actually work through your proofs in general always, but especially so when you're dealing with greedy based approaches. So now let's go back to the drawing board and try and find a function that actually works. Another natural way of trying to prioritize files that have short lengths, high frequencies, and deprioritize ones that are longer or are accessed infrequently is to actually take the ratio of these two values. So let's think about L over F. So this also has this sort of behavior, and this time it turns out that this approach would actually work. So let's make the approach concrete. What I'm proposing is that for every file, you make a note of its length to frequency ratio, okay? And then you sort the files in increasing order of these ratios. So the files that have the smallest value for L over F would come first, and so on. At this point, we want to actually argue that an ordering obtained in this fashion is actually optimal. And in particular, we want to prove this lemma here, which says that the total cost is minimized when you line up the files in the fashion that we just described. And this is just being said in notation here. So just like before, we are going to attempt to prove this claim using the method of contradiction, which is to say that suppose there is an ordering that is strictly better in terms of total cost when compared to the output of our greedy algorithm. So we are going to work with this hypothetical better than greedy ordering, and we are going to try and morph it into another one which has an even better cost, which would contradict the presumed optimality of the hypothetical ordering. So suppose we start off with some ordering pi, and we know that this is not the greedy ordering. We know that this is different from the order that's output by our algorithm. And remember that we are making this assumption for the sake of contradiction. Now, what can we make of an ordering like this? An ordering pi, which is supposedly optimal and different from greedy. Well, let's just look at the files as they are ordered in pi from left to right, and let's pick out the first point where this ordering deviates from the greedy order. So you go from left to right, and maybe for a while pi has the greedy behavior. The L over F values for these files are steadily increasing, but at some point that does not happen. And this point has to come because if L over F values are increasing all the way till the end, then pi actually matches with the greedy order and would have the same performance as the greedy output. But that's not what we have assumed here. So at some point, you're going to encounter a situation where you have two files sitting next to each other, with the preceding file having a larger L over F value compared to the file that comes just after it. So in this picture, let's say that A is the file that comes first, has a bigger L over F value compared to B, which is the file that comes just after it. Now, just as we did when we were analyzing the greedy algorithm for optimizing the expected cost, we are going to do a similar stunt here. We are going to say, let's come up with a modified ordering pi prime, where we basically stick to looking a lot like pi, with one difference, and that difference is that these two files which are in the spotlight right now, A and B, are going to be swapped. So this is what our new ordering looks like, and the way we are going to derive our final contradiction is to say that this new ordering that we have constructed based on pi actually has a cost which is smaller than the cost of pi. And that will contradict our assumption that pi is an optimal ordering. So let's go ahead and analyze the cost of the new and the old orderings. So in fact, if you just look at this picture, you can probably see that the cost that you pay in the new ordering, and let me call that pi prime here, the cost that you pay here is going to be extra for the file A. You're going to pay an additional cost of LB times FA. So for every time that you access the file A, and that's going to happen FA many times, you're going to have to go over the file B, which you didn't have to do before, right? On the other hand, a cost that you had to pay previously that you don't have to pay now is the cost LA times FB. So LA times FB represents the amount of hopping that you had to do in pi to access the file B. So you access the file B, f of B, many times, and in each of those accesses you had to hop over the file A, which is something that you don't have to do now. If you think about it for a minute, you'll see that all the other costs are exactly the same, but what's happening in pi prime is that FB minus LA is reduced and FA times LB is added compared to the cost that you had to pay in the order pi. Now the question in front of us right now is this a net increase or a net decrease in the cost? Well, to be able to appreciate which way it's going, and of course we are hoping that this is a net decrease because that's what we want to establish. We want to establish that pi prime actually achieves a smaller cost than pi. To see this, we have to go back to what we have assumed about the ratios. So we did say that A has a bigger L over F ratio compared to B, which simply means that LA over FA is greater than LB over FB, but that just translates to FB times LA being bigger than FA times LB, which also tells us that the net change in cost is actually negative, which means that we have an improvement in the cost when we slide over from pi to pi prime. So overall, we have a better ordering now, an ordering that is better than a presupposed optimal ordering, which contradicts the optimality of pi. And therefore, greedy actually works. So that concludes our discussion about the file storage problem, this time with frequencies and the situation where we were trying to optimize for the total cost. Next time, we will see a scheduling problem involving dance classes. I look forward to seeing you in the next video.